what I need to do to finish off today is to actually now talk about measuring angles in a slightly different way. So let me come down here. So I want to talk about radian measure of angles. So it says, in many mathematical topics, and especially in calculus, we're better off measuring our angles in radians rather than degrees. So all of the formulas that we have in calculus all are true only if the thing's measured in radians. So therefore we better get our head around radians is the thing. So what is a radian measure of an angle? And it goes like this. It says, the angle formed by the arc of a circle of length 1. So what we're saying is, draw yourself a circle and imagine that you've got a sector or an arc of that circle, and that arc is of length the same as the radius of the circle. So that arc is of length r. So here the arc length is 1 radius sitting here. If that's the case, then this angle here at the centre is defined to be 1 radian. So the angle at the centre is 1 radian. In there. And we use 1 with a little superscript c. C for circular measure is our symbol for radians in there. As I say, it's not an immediately intuitive way of measuring angles, but again, somewhere someone's worked out that if we measure angles this way, everything works out much nicer later on. When I say much nicer, I mean much, much nicer. Okay? It makes our life so much better later on that it's worth doing. So, let's try and get a handle on this radian measure. Now, if I were to draw an arc, so the arc equal to the entire circle. So if I were to, let me just draw another circle here. If I were to, I didn't even need axes, but anyways. So if I were to start there and to go all the way around, then I know the length of that is just the circumference of the circle. And the formula for the circumference of a circle is 2 pi r. So that's the length of that arc. I know the angle subtended at the centre by that. So the angle, and if I put it in degrees, at the centre is 360 degrees. It's 1 full turn. If I start there, go all the way around, so that angle there is 360 degrees. Gone all the way around. Now, what's that angle in radians? Let's think back to what we've got here. It says, if the arc length is 1 radius, then I have 1 radian. If the arc length happened to be 2 radius, so if I came around here, and that's 2 radians, then that angle sitting in there is 2 radians. Right? So the angle, the size of the angle, is the number of radii that the length of the arc is. Now, how many radii are there in the full circle? I had to multiply by 2 pi. So the angle at the centre is going to be 2 pi radians. So the same angle in radians it's the number of radii that needed to get me to the full length of the arc. And so that is in fact 2 pi radians. And so we now have a way of converting from radians to degrees. So therefore 2 pi radians is the same as 360 degrees. And if I divide both sides by 2, I have pi radians as 180. Sitting in there. So from that, we can do all our conversions. So let's just say that's the important thing. Sitting in there. Pi radians is the same as 180 degrees. So what you need to do, and what we're going to attempt to do now, is we're going to start to get you to become conversant in radian measure. Initially what you will do is you'll get a radian, you'll convert it to degrees, you'll do all your work, then you'll convert it back. Eventually you'll become fluent enough to work in radians natively. Okay? It's like learning a new language. Initially you've got to convert, but eventually you become good enough. Okay, so we've got our L plates on at this stage, so we're going to convert. So let's do it. So write the exact value of the following angles that are in degrees. Let's put them into radians. So we start off with our standard thing. Pi radians is 180 degrees. Now, if I divide both sides by 180, I will have, that tells me that 1 degree is pi on 180 radians. And that's the exact conversion. If I wanted to do an approximate conversion, pi, if you got on your calculator and went pi divided by 180, you'll get a number that's about 0.0175 or thereabouts. So what that's saying here is that 1 degree cuts off an arc that's about 0.0175 as long as the radius. Let me draw a picture of that, just so as we've got it straight. So if I have a circle here and it has a radius of r, if I have now this is clearly too big, but imagine that that's 1 degree. What that's saying is that this arc length here is about 0.0175 r times r in length. That's the length of that arc sitting there. That's how many radii are cut off by that angle. Okay, that's our interpretation of that little formula there. Okay. 1 degree is small, of course. Actually, I'll leave that up. So, I can now do these. 30 degrees is going to, if 1 degree is pi on 80, 30 degrees will be 30 times pi on 180 radians. Now 30 into 180 is 6, so that is the same as pi on 6 radians. That's the exact value. Sitting there, exact. B. 45 degrees is 45 times pi on 180. 45 into 180 goes 4 times, so that's pi on 4 radians. So we've got the swing of these. 60 degrees is 60 times pi on 180. So that's the same as pi on 3 radians. "90 degrees is 90 times pi on 180. So pi on 2. Now in this case, 120 doesn't go into 180 nicely, but 60 goes into that twice. 60 goes into 180 3 times. So this would be 2 pi on 3 radians for 120. That's as simple as I can write it. And 270 degrees would be 270 times pi on 180. This time 90 goes into that 3 times, 90 goes into that 2. So that would be 3 pi on 2 radians. But you can see the way to do the conversion. Start with pi is 180 degrees, pi radians. Make 1 degree the subject, and then you just multiply by whatever the factor is. In this case, these all simplified down nicely because I chose nice simple angles over here. That isn't always the case, of course. Okay, we choose the ones here that are easy, then I give you the harder ones to do. No, that's not true. Let's do this. Let's do some where the angles aren't so nice. So it says, find approximate values in this case. So once again, 1 degree is pi on 180 radians. So here in part A, 312 degrees is 312 pi on 180 radians. That's the exact value. And then what you do is you get your calculator out, go 312 times pi, divide by 180, and I get something like 5.445. To 3 decimal places. Five radians. Does that seem reasonable if we were thinking about it? And I guess in a sense it does. In that, I need to bring this over here again. In that, if I have my circle here, we've said if I go round 360 degrees, 360 degrees is 2 pi radians. 2 times pi is about 3.1, so this here is about 6.2-ish, about. So 6.2 radians takes you a full turn. 312 degrees is not quite all the way round, and we're not quite up to 6.2. So that seems like a reasonable answer to me, sitting in there. Minus 47 degrees is just minus 47 times pi on 180. That would be the exact answer, but get your calculator out, minus 47 times pi on 180. This turns out to be quite small, minus 0.820, radians. Again, to 3 decimal places. See it in there. Question?
Yeah, just when you said minus radians there, I was just thinking, was it not always just be a positive because you're going around the circle, or is it just denoting that it's going back, it's going counterclockwise?
That's right, we're going that way.
That's just the point they're making, is it?
Yes, yes indeed.
Essentially it's...
Positive means go counterclockwise, negative means go clockwise. That's correct. Okay, that's just the convention. Yep, good one. So let's put that in there, i.e. clockwise.
Essentially it's the same as 360 minus 47, 300, whatever.
Yeah, 13. Yeah, that's right. That's right. That's correct. Yep. The reason we wanted negative angles is again so that when we come to functions, the domain is all real numbers. Okay? Makes life so much easier when we've got a domain of all real numbers. Yeah, it's in relation to what's coming up. Yeah. Yeah. All right. So we went from angles in degrees to angle in radians. Let's go back the other way now. So we start again. We have pi radians is 180 degrees. So that tells me that 1 radian is 180 divided by pi degrees. And that turns out to be something like 57 point, I didn't need to go that many decimal places, but something like 57.3 degrees in there. So if we were to go back to this diagram here, this angle there of 1 radian turns out to be about 57.3 degrees. So to cut off an angle, to get an arc there that's the same length as the radius of the circle, that angle in the middle has to be around 57.3 degrees to do it. That's what it says. So let me put that back over here. So, if 1 radian is 180 on pi, then 5 pi on 3 radians is 5 pi on 3 times 180 divided by pi degrees. And you see, in this case, the pi's cancel out quite neatly. 3 into 180 is 60. 5 60s are 300. So that converts to 300 degrees. Something like 7.21 radians. Well, 1 radian is 180 on pi, so this is 7.21 times 180 on pi degrees. So you can do that, and in fact, if I did that, I got here 12,978 on pi degrees. That would be the exact answer. Now, the thing is, that doesn't mean very much. To me, seems too big, is it? 1, 2, 180. Nope, okay. And so, as an approximate answer, it's 3. I think that should be a decimal place in there. Can someone just do that on their calculator quickly for me? One. Yeah, no, what's 7.21 times 180? 0.8, yeah. Okay, so that should then be 413.10 degrees, and that seems right. Because as we said before, about 6.2 radians is a full circle, so this is a little bit more than a full circle. So 413 seems about right. Yep. So that needs to be a decimal point sitting in there. And so that would be our approximate answer sitting in there. So when you're doing your conversions, all you have to have is this sitting in front of you, and you can work from that each time. Okay. If you're converting from radians to degrees, make it 1 radian is such and such. If you're converting from degrees to radians, make it 1 degree is equal to whatever. That's all you have to do. So it says, okay, so let's find the exact value of these trig ratios where the angles are now measured in radians rather than degrees. So you have 2 ways of doing it. You can say, here's an angle, convert it to degrees, work out the trig ratios and hence go that way. Or we could just work natively in radians. So let me work natively in radians in here. So in here, go back to our special triangles. Our special triangles that we had. One of them was a equilateral triangle. I'll do it here. One of them was an equilateral triangle of side length 2. Then we cut it in half. So this was our right angle triangle here. We had a right angle there. That was of side length 1, that was of side length 2, and by Pythagoras' theorem that was of side length 3. And our angles here, this one turns out to be pi on 3, and that one is pi on 6. And I guess we should go back and have a look to this first lot of conversions we did. That might help us here. If you have a look, 30 degrees is pi on 6, 60 degrees is pi on 3, and in here the angles were 60, 30 and 90. So pi on 3, pi on 6, and I guess if I wanted to I could also say, look, that right angle there, that's pi on 2 in there. So there's your triangle written in radians rather than degrees. And so now I can say, what is the sine? Oops, that's not the right triangle. I need the other one. Okay, so the other triangle was this one, where we had side lengths 1. So we've got a right angle, that's pi on 2. Had a side length of 1, 1 and square root of 2 via Pythagoras' theorem. And if we have a look, 45 degrees is pi on 4. So both of those angles are pi on 4. In there. So there are our special triangles, now with radians instead of degrees, and therefore I can just say the sine of pi on 4 is the opposite over the hypotenuse. So the sine of pi on 4 is equal to 1 on root 2. And of course we could have also gone the other way and said, so pi on 4 is 45 degrees, and the sine of 45 degrees is 1 on root 2. Doesn't matter which way you go. And we can do the others now as well because we have the triangles to go with it. So that was A. B says work out the cosine of pi on 3. Cosine of pi on 3 is adjacent on hypotenuse. So that's the same as the cos of 60 degrees. And the last one I've got here, tan. All right, so this one's a little bit trickier. It says minus pi on 6. So if we go back to our right angle, back to our plane, and we've got the first quadrant, second quadrant, third quadrant, fourth quadrant sitting in here, we could do two things in this case here. I could think to myself, I could use that mnemonic that I mentioned before, all stations to, and we hate Cardiff, but we'll put Cardiff in there. Apparently we don't like Cardiff. I don't know, why don't we like Cardiff? Anyway, no response. And so in here, this tells me that all the trig ratios are positive there, sine is positive in the second quadrant, tan's positive in the third quadrant, cos is positive in the fourth quadrant. So pi on 6 is an angle that's here. All right, that's minus pi on 6 in there. So we're in the fourth quadrant, so the tan will be negative. And so I can say tan of minus pi on 6 is the same as the negative of tan pi on 6. In there. Now the tan of pi on 6 is the opposite over the adjacent. So I have minus 1 on the square root of 3. Yep. I guess the other thing no, I'll leave it at that. I'll leave it at that. The other thing you could have said here, look, I'm in the fourth quadrant. The y-coordinate is negative, that's sine. The x-coordinate is positive, that's cos. So sine divided by cos is going to be negative. You may have thought that. That takes a long time to think that. Okay, so either way we get minus tan pi on 6. Okay. And to finish off the day, as I said, I was talking about radian measures, but there's a couple of little formulas that follow immediately when we have things measured in radians. And it says the length of the arc of a circle of radius r, so a formula for this length sitting here will be S, the rate is the angle in radians multiplied by the radius. And that comes just from our straight definition of radian measure. So I'm not even going to, I've got it in a box, but I'm not even going to highlight the box because that's just a formula. It's not overly important. It's a formula, we can use it when we need to, but there's nothing particularly amazing about that. The important thing is that your angle needs to be measured in radians. If it's measured in degrees, then you'll need to convert it to radians to use it. And the other formula that we've got is that the area of a sector of a circle, so that's this area in here, it's a half theta r squared. And I guess, where does that formula come from? It says essentially the area of the sector, the ratio of the area of the sector to the area of the circle is equal to the ratio of the angle to the angle for an entire circle, which is 2 pi. And so therefore the area of the sector is theta on 2 pi times the area of a circle, which is pi r squared. And so that gives me, the pi's cancel out, and I'm left with a half theta in radians r squared. So they're just a couple of formula, and they're easy to use. I think you just substitute straight in, so we'll do that. So that formula, as I said, is just saying that the area of this, the ratio of that to the area of the whole circle is the same as the ratio of the angle to the full turn, to the full 2 pi radians. So it says find the arc length of the sector and the area of the sector in the following circle. So here, the arc length. So S is equal to theta in radians times R. I have 115 degrees, so I will convert that to radians. 115 degrees times pi on 180. Just remember, pi radians is 180 degrees, so 1 degree is pi on 180 radians. So here, the arc length, this length out here, is 115 times pi on 180 times the radius, which is 3.2. And I did that on my calculator and got something like 6.4. So that length there is 6.4, about, from there to there. And to find the area of the shaded bit, the area will be a half times theta in radians times the radius squared. And that came out to be 10 point, approximately to 2 decimal places, 10.28, and I guess units squared, whatever the units are. That would be the area of that shaded section there. So to use those formulas, it's just a matter of substituting in and making sure your angle's in radians.